And we're back with another one. This is the Diabolic vtutor. We're just going to be carrying off where we left off from last time. Basically doing more mixed topics. Last stream I didn't cover any logarithms, so this time we're going to hit a few of those. Should be good. So let us get started. Jumping through the problems. Well, I gotta find the problems first. And apparently I'm in the wrong page. Whoops. Alright, so let's just start off with something a little tedious. Just as a warm-up problem. So this particular problem isn't super difficult or anything like that. It's just going to be, well, you'll see. You'll see what it is. Alright, and there's problem number one. Lots of distribution to do. We're just simply solving for x. There it is. Just take a quick peek. We have this thing right here. So lots of distributive property. So a little mechanical, boring mechanics, but that's fine. Just a warm-up problem. Take care of the inner parentheticals first. So distributive property for those two. 6x squared plus 10x. So this is the distribution for this piece right here. Copy paste to plus 2. I almost forgot the x to the 10. Whoops. There we go. Alright, let's just make sure everything is correct. Yes, yes. Okay. Then we have x on the outside as equal to 2. So nothing too tremendously difficult, just fairly straightforward distributive property. So we're going to have 6x cubed plus 10x squared plus 2x. And we're going to subtract this 2 from both sides just to set up the zero product property. So minus 2 from my hand side and then minus 2 from the left hand side. Thereby getting this one right here. Okay, good to go for that one. As you notice, they all have even coefficients, so therefore just fact out the 2 from each of those. And we can clear the 2 by dividing both sides by 2. But I'm just going to leave it here for a moment. So again, nothing tremendously difficult. It's just the integral problem. Alright. So we have this polynomial right here. Very simple. It only has factors of 1 and factors of 3. So 1 over 1 comma 3. Sort of plus or minus situation. So again, not too bad. This one calls for synthetic division probably. I don't. Factor by grouping isn't really obvious, so let's just jump straight to the synthetic division since the numbers are very simple. So 3, 2, 1, 0. All terms are present and accounted for. So let's extract the coefficients. Descartes rule of signs, I can see right away there's only one sign change, so we should test the positive candidate first. So 1 is a very straightforward candidate, so drop the 3, multiply. Oh, okay, this is not going to end well. Here's the reason why it's not going to end, because the numbers are going to snowball just a little bit. Summate, product, summate, product. As you see, there's a remainder of positive 8. So 1 was not the way to go. So we have to test 1/3. 1/3. That should work. So drop that, product, summate, product, summate, and lastly product, of course. It's going to work out perfect. So therefore this is a 0 of the function, so therefore x minus 1/3 is a factor. This is a leftover quadratic because we are going from x cubic, we're dividing out one of these factors, so it becomes x squared. That's the quotient. But each of those terms has a 3, so let's factor out the 3 from those, which will make further factorization easier. And then this one we will distribute to this one just to make it look nice. But as usual, you don't have to distribute this into here. You could just simply leave it in front. But I'm going to distribute it. This one, well, yeah, I think this is a perfect squared trinomial. Half of 2 is 1, and then 1 squared is indeed 1. So this is a perfect squared trinomial. So like that one. But let's consolidate this one with this one. There we go. Yeah, there's a 2 up here. I'll just copy paste it for good measure. Alright, I think we are done with the factoring. So this is fully factored form. We're supposed to solve for x. So we have 2 unique solutions. So solution number 1, x is equal to -1, which produces this as a 0. Verifying 0, which checks out with the 0 product property. And then this one, it could be positive 1/3. So 2 solutions for the situation, and then we are good to go. Yep. Let's get the overall problem. There it is. So not too bad, just a quick warm-up. Moving on, of course. Let's find some interesting problems. Okay. Well, let's do this one. Unfortunately, I do need to draw it out. XY axis, it's a graphing problem. So we have 1, 2, 3, 4, -5. And then we have 1, 2, 3, 4, +5. And here's how the old graph looks. There's a 0 right there. Downwards, and then it's cut off from the viewing window, and then we have the graph going upwards like so. Alright. So the question, or rather, oh yeah, it is a question. So if f of x is degree 5, is a degree 5 polynomial. What could be the equation of f of x? Alright. Look at this graph right here. The orange graph is going to be f of x right there. So there it is. There's the question. There's the graph to the left, and then there's the question right here. Degree 5 polynomial. Do recall what that means. It just means that we have a polynomial function, and then the leading term, if you arrange it in order, will have degree exponent 5 right there. So we don't know what the coefficient is right off the bat, but we do know that this thing is going to be the highest exponent for any of those terms in this polynomial f of x. So let's just start with the zeros, of course. So we have 0 number 1, which is right here. And then we have 0 number 2. So we only have 2 unique zeros. So what is 0 number 1? The 0 number 1 is at -2. And then 0 number 2 is at +2. So we can convert those into factors. So if the 0 is a 2, then the factor is x minus 2. And then if one of the zeros is -2, then the factor is x minus -2, which is just going to be +2. Now, we don't know the multiplicities of those ones, but we do know that this is even multiplicity, so I'll write v for even. Not e, because e is a natural number, so we'll just put v. That feels weird. It feels like velocity. Let me use n. So n right here, where n is even, and then we have an odd multiplicity right there. Let's put m. All right. And there is a coefficient in the front. We don't know what it is, and let us not commit to anything. And then we'll have f of x. Alright, so that's all we know for the situation just by looking at the zeros. Again, this one right there, and then this one right there. This one has to be even multiplicity because it has the parabolic motif. And then the red factor must have an odd multiplicity because it's the pierce through situation. And we are told in the beginning that it is a degree 5 polynomial. So if you summate those two numbers, then we need to generate an exponent 5 in the end. And that's essentially what we're going to follow up from. Okay. And to make note of the end behaviors, this is a down upwards situation. So that means that we have an odd exponent, which is good because it agrees with the problem right here, degree 5. So we're going to have degree 5, and then we're going to have a coefficient in the front. It needs to be a positive coefficient because, again, we're going from down to upwards. So if it's a positive value in the front, I'm just going to put this plus in the front. Because if you raise a negative value to the power of 5, you get a negative value. If you raise a huge positive value by 5, you get a huge positive value. All right. So I think the simplest thing we can do is this one needs to be even. So it could be 2, it could be 4, it can't be 6 because 6 as a multiplicity will be exceeding the degree 5. So we'll cut it off at 6. We'll cut it off at 4, I mean. And then for the odd multiplicity right here, it could be number ranging from 1 to 3 to 5. Not 5, because then we wouldn't have any numbers left over for this particular factor. Because, again, we need to satisfy degree 5 requirement. So that ain't it. So in terms of the workable ones, we can go with 2 and 3, or we can go with 4 and 1. I'm going to pick the kind of the intermediate option and just pick those two. So I'm going to pick degree 2 and a degree 3 because nothing else is really specific to this particular function. Alright. And to keep things even simpler, I'm going to take this a right here. I'm just going to put it as a positive 1. There is no real reason to do it, but I just want the lowest possible coefficient in the front. You can put plus 100 if you want, because again, there's no y-axis. There aren't any hash marks on the y-axis, so no need to worry about that. So again, I'm going to keep it as low as possible, positive 1 for the a value. Alright, so let us commit now. We're picking exponent 2, so we have x plus 2 to the power of 2. And then for the red one, we'll pick exponent 3. A value, I'm just going to leave as invisible positive 1, and then we just declare f of x. Alright, that's it. That's one potential answer for this particular situation. Another probably equally as popular, you could choose 4 if you wish. So we could do x plus 2 to the power of 4 with the even multiplicity, because again we have this parabolic motif. And then for the red one, we'll just downtick that one to 1 exponent. Exponent 1. And we'll just copy paste f of x. So either of these should be valid answer. So we'll just put or. Those will probably be the two most popular ones, but again, you can technically have many more. You could put a 1/2 here if you want. But you cannot put -1, for example, because the end behaviors are downwards, upwards, not upwards, downwards. But again, I should just choose positive 1 because it's the easiest one to do. Okay, so pretty straightforward, just a typical graphing problem. Given the zeros, you can convert them into factors, and just make sure that the end behavior agrees, and you satisfy the degree requirement if it's stated. But we're done. And we have another degree polynomial type of situation. But let me jump to a log function problem just for the mix-ups. Sounds like a video game or something, the mix-up strats. Okay. Start off with a fairly straightforward log problem. So we have log base 5. I hope I didn't do this one already, but if I have, it's okay. I didn't exactly keep track of which problems I've done for some of these. So, apologies if you've already seen this one. So not too difficult. We have base 5 with the unknown, but then we have a base 3 with a known value, and when we know that we can break up the 81. Because 81, we can get 81 to match base 3. So let's do that first. So 88, we can change that into 9 times 9. And that one we can change into 3 to the power of 4. So for the situation, we can transform it into log base 3 of 3 to the power of 4. And an exponential slammage, we take that 4 and slam dunk it down in the front, thereby getting this one. But recognizing the log base 3 of 3 is just 1. So this whole thing transforms into times 1. So let me clear this one right here. So again, this whole section right here, right hand side, transforms into 4. And we'll copy paste this entire left hand side. So we do have some options here in terms of how we're going to proceed. We can expand the left hand term, or we could just take 5 to the power of 4 equals argument. I think that's much simpler. So let's do that one. 5 to the power of 4 should be equal to the argument 125x. So here we are. And at this stage, you can distribute this one, but rather than do that, I'm going to break this one down. This is just basically 5 times 5 times 5. So 5 cubed. And of course, classic exponential situation, we're going to divide both sides by 5 cubed. Cancel, cancel. Thus, do we get x is equal to subtraction rule of exponents 5. And we're done with that one. Pretty straightforward so far. Oh, I already did this one. Let me move on real quick. Finding appropriate problems for this mixed situation. Of the one that's graphed. That's -5, so we have 1, 2, 3, 4, 5. We'll put 6 for good measure, 6, and then here will be -6. No commitment to the y-axis, but let's graph. So we have a 0 at 1 and 4. 1 and 4. So off the page and then something like this. Exaggerating it with this downwards trend, so it does loop back like this, but it's cut off screen. And then we have a parabolic motif at this portion right here, -3. Yeah. Alright, let's put the viewing window. Okay, gorgeous. And this function is referred to as h of x. So that's the graph, and then here are the options for the situation. We have option A. That's going to be x minus 3 squared times x squared plus 5x plus 4. Option B. X squared minus x minus 12 times x minus 1. Option C. It's an x squared plus 2x minus 3. Multiplied to x squared minus x minus 12. And then option D. X plus 3 cubed. Times, oh, two more things, interesting. So times x minus 1 squared. And x minus 4. And again, the question is, which of the following, if any or more, could be the equation for h of x? So I don't want to write that completely. So I'm just going to put h of x with a question mark. If any. We could also have multiple answers for the situation. But here we go. I don't know if everything's off to the right hand side. Let me move everything over real quick. Okay. Alright, so quick check. We have a downward situation. So this is going to be x with an even degree multiplicity. So the leading term is going to be even. I think I misspoke, even degree multiplicity. I mean, in expanded form for this particular polynomial, the leading term will have an even exponent, even degree. Indicate as such, and since it's pointing downwards and downwards, that implies that we have a negative in the front. So that one is already pretty good for disqualifying some of these options. Let's just make note of the zeros as well. This one is a zero located at -3, so the factor is x plus 3. It's going to have an even multiplicity. So I'll write it like that, and then this one has an odd multiplicity. That particular zero is at x is equal to 1, so that means the factor is x minus 1. With, again, odd multiplicity. And then that one right there is a strike through, so therefore it's odd multiplicity, x minus 4 as a factor. Odd multiplicity. So we're going to have something like this reconciled with this, and we're going to check each of those four. So we can already see that A is going to be wrong without even checking the zeros, because partial distribution, we're going to get x squared times x squared with positive sign in the front. So again, we get a positive x squared from here. This is already positive x squared, so when you multiply them, that's positive x to the power of 4. So from just by looking at the end behaviors, we can eliminate this one. And the same is true for option B as well. So we have x squared times x, which gives us x cubed for the leading term, positive x cubed, but this is going downwards, downwards. Positive x cubed would be going downwards to upwards. So we've disqualified yet another answer. Choice B cannot be correct. And then we have choice C. We have x squared here, and we have x squared there. So if we do partial distribution, we're going to get x power 4 with a positive in the front. So for the same reason why we eliminated choice A, we could also eliminate choice C. So do we have no answers? So we have 3 distributed to x, partial distribution, x cubed. Partial distribution is x squared. And then we have an x right there. And of course, we get another positive in the front. Add up the exponents, invisible 1, we get exponent 6. So this one is going to be upwards, upwards, end behaviors, which is inconsistent with this downwards, downwards. So D is also wrong. So none of these choices, if any, and none of them are. So that's nice. Nothing to circle. We don't even need to check the zeros, really. We just check the end behaviors. But let's make it a little more interesting, right? And to make the problem situation more interesting, I'm just going to arbitrarily put negative signs in the front of each of these problems. So here's what's going to happen. This problem is already done, but just to further investigate. So here's what I'm going to do. I'm going to switch this one around real quick. So we're going to do 3 minus x. And on this one, I'm going to do x minus 1 minus x. And for C, I'm just going to arbitrarily slap on a negative value in the front, because I want this problem to be a little more interesting. Now this one I'm going to swap, and this one I'm going to swap. So this one will be 1 minus x. And this one will be 4 minus x. Alright, so now that I've changed the problem, let's see if that does anything for our answers. Alright, so we can't eliminate choice A right off the bat. Just kidding, we can. So how come we can eliminate choice A right off the bat yet again? Despite there being a negative right here, well, if you use partial distribution, this thing still ends up being x power 2. And partial distribute to this one, it's still going to be x power 4. Positive. This is going downwards, downwards. So choice A is still wrong. And choice B is a little more interesting, but it's still eliminated for the same reason as before. This is x power 2. Regardless of the sign in the front, this one, if you do partial distribution, your leading term is going to be x power 3 with a negative in front. But this one is inconsistent with this downwards, downwards trend regardless, because cubic functions are either down, up, or up, down for the end behaviors. In this case, because of this negative, it's this one right here, but it doesn't matter. So because of this reason, B is still eliminated. So this one is a little more interesting now. We have a negative in front. Distribute partial distribution, we do in fact get the negative x power 4, which is finally consistent with this end behavior. The question is, does it have the right zeros? Let's see. So factorizing that, let me use a different color. Alright, so factorizing this one, we have a negative in front still, and then factors of 3 is just going to be 3 and 1. The larger of the two is positive, so it's going to be this one is plus and this one's minus. And of course, factorizing this one as well, we just have a 3 and a 4. So it's going to be x with a 3 and then x with a 4. The signs are different, and the larger of the two magnitudes is negative. This is the larger of the two, so that's negative. This is a smaller, so it's positive. And these two, we can consolidate it. We can consolidate them together and have x plus 3 squared, comma, or not comma, I mean times x minus 1 times x minus 4. So I think this one actually looks good. Let's double check. So we specified this one has to be even. Yes, it's even. This one has to be odd. Yes, that's odd. That one also has to be odd. Yes, that one's still odd. So perfect. We have a negative in front. This is a negative in front, so this one qualifies. So choice C, again, the modified version of choice C is actually good now. So for this modified problem, C is good. And of course, checking D. Is D a valid answer choice? So we have a negative here, but that gets squared for the partial distribution, so it becomes positive x squared. Partial distribution, we have x power 3, and then this one is a negative, so times negative x. So this one does, in fact, give us an even degree exponent with a negative in front, which is good. So it's consistent with these two end behaviors, so good to go so far, but we need to test the zeros, of course. So what are the zeros of this? It's already written for us. This is an odd multiplicity, but it's supposed to be an even multiplicity. So that, as we concluded earlier, because this is a parabolic motif, this is not a parabolic motif. So choice D is eliminated just straight from this one. And this one also eliminates it, but we don't care. This one is actually consistent. So this doesn't work, and that doesn't work. Alright, that was pretty clean. So technically that was 2 problems in 1 problem, but that's okay. Done with that one. And it seems I lost my bookmark real quick. Okay, hopping back to the log problems. Hopefully we get more difficult problems. Alright, here we go. So we're going to have log base x of 5x. And that is subtracting 2 times log base 6, I think. Log base 6 of 2. And that's equal to log base 6 of 9. So not particularly difficult, I don't think, off the quick check. This is base 6, this is base 6, so we're going to probably move this over to the other side to combine it with this one. This is base x. That's kind of weird, but it shouldn't be that weird, I think. So let's carry out the plan of attack by adding this to both sides. So we're going to get, after cleanup step, we're going to get log base 6 of 9 plus 2 times log base 6 of 2. Copy paste this one right there. There we go. We cannot combine these ones straight off the bat because there is a coefficient in the front of the second term, so we're going to have to reverse exponential slammage that. So take that 2, move it back as an exponent. I'll just write a new one. So there we go, and then of course this is just simply a 4, so 2 squared is 4. So I'll delete this 2 squared and just put a 4. Now that we have that, we can finally combine the right-hand terms. This one is combinable with this one because of the same base in the presence of an addition. So just multiply the 2 arguments. So 9 times 6, I'm sorry, what did I say? 9 times 4 is 36. Alright, this side's just copy-pasted. Okay, and of course this is also a resolvable situation. 6 to the power of what number gets us this 36? It must be 2. There it is. And this I just copy pasted yet again. Alright. And then, of course, straightforward, we're going to take this one, raise it to the power of 2. It should be equal to the argument. So again, x to the power of 2. Should be equal to what? The argument, 5x. So we have the situation here. Best practice is just to move it to the other side. You can technically divide both sides by x. We'll talk about that in a moment. but let's just move it over to that side. So we're going to get x squared minus 5x is equal to 0. Factor this junk, we're going to get x times x minus 5. Thus, 2 0 candidates. So we have x is equal to 0 and x is equal to positive 5. Never ever get too excited. Make sure you double check for extraneous solutions. So let's see. Here's the original problem right there. Are these valid inputs? No, the 0 is not valid. If you plug in 0, you're going to get log of 0. And log arguments, they don't take in zeros, so therefore this one ain't going to work. So no 0. 5 is going to work out because you're going to get a positive argument if you plug in 5. And this base is also positive, so the 5 is good to go. So just one solution for the situation. There it is. Let's just do another one, just so I don't have to keep flipping back and forth. So we have log base 3. Log base 3 of 54. All over 3 log base 4 of 2. Subtract log base 3 of x. All over log base 4 of 8. So nothing too fancy right here. And is equal to 2. I don't know why my penmanship is atrocious, right? It's kind of going downwards. That's fine. Let me move this. Okay. So there's the problem. Take a quick survey always. We have a base 3, base 3. This one has a constant. This is unknown. This is constant. This is a constant. So we could probably resolve these ones and probably resolve this one. The 2-1, nothing special is happening there. So let us mess around with these parts first. Let me think about this. Well, the first thing that I can immediately see is we can reverse exponential slammage this. Take this exponent, move it back here to the 3, and then this will become 8, which matches this one right here. In fact, those two will match up. So let's do that first. And for the sake of expediency, I'll just copy the whole thing. All right. Well, this one is not part of the original problem. The 3 was in coefficient, not the exponent. So I took that coefficient and then reverse exponential slammage. It's now right there. So 2 to the power 3 is just 8. So let me clear that. And now that we have fraction number 1 minus fraction number 2, then we can combine those two by subtracting just the top portions and maintaining the same denominator. So we have log base 3 of 54 minus log base 3 of x. All over log base 4 of 8. That's still equal to 2. So a few things we can do to make the situation even nicer. We can multiply this to both sides, tossing it to the other side. Because typically, again, when you work with log functions, you want to isolate the bases. Keep the same bases together, and then the bases that are not what you want, you just toss them over to the other side, or you try to rework them using change of base rules. I don't think we need to use change of base for this problem, but we'll see. So again, we're going to multiply this to both sides, and then we're going to condensate these two terms together. So let's, I guess in no particular order, we'll multiply both sides by log base 4 of 8. Log base 4 of 8. So thus, well, we cancel this one with that one. And this one condensates, since we have the same base, just this is a minus, so we're going to find the quotient of the two arguments. So it's going to be 54 over x. I'll put parentheticals. maintaining the same log base 3. All over, what happened? Oh, it's just over 1 since we canceled this one with this one. So I'm going to omit the denominator. But there's always an invisible 1. And copy paste this side. You know what? We can work with this one just a little bit more. We could take this exponent 2 and then slam dunk that up there. So this whole thing, we can transform it into log base 4 of 8 squared. And then 8 squared is simply 64. But wait, 64 is just 4 to the power of 3. Why 4 to the power of 3? Because it matches the log base. So we could take that 3 exponent and slam dunk it down in the front. There we go. So, cleanup step, let's start moving things closer. So that is what we have. This one is further simplifiable. Anytime you have matching base with the argument, this whole thing cancels to become 1. Alright, we're going to resort to standard procedures. This base to the power of that number equals argument. So 3 cubed is equal to the argument. We're going to do the old switcheroo, so we're going to swap this denominator with this one. Because, you know, you could just do this. That would be the formal step. I might as well just write it out. So this one cancels with this, and then this cancels with that. So thereby we have 54 over 27 is equal to x. That's nicely divisible, so we get clean 2, so x is equal to 2. Check for extraneous solutions, of course. Can x equal 2? Yeah, no domain conflicts right there, so we should be good to go. So x is equal to 2. Confirmed. Let's take a quick zoom out. There we go, the entirety of the problem. We're going to do one more log problem before we jump back to logs later. So we have 3 to the power of log base x of 4. And that is equal to 9. Okay, multiple strats. We just have an exponential problem with the log function on it. This is a classic situation. We have base 3 on the left-hand side. We have base 9 on the right-hand side, but this is easily transformable into 3 to the power of 2. Now that the bases are matched up, just drop the base. So exponents must be equivalent. Standard x to the power of 2 equals 4. Thus, that we get 2 answers potentially. So if you take the square root of both sides, x could be equal to plus or minus 2. Because we're transitioning from even exponent to odd exponent. So 2 potential answers. Make sure you double check them, of course. Can we have a -1 as a base? No. So that one's extraneous. Can we have 2 as a base? Yes. So this should be the only good answer. So good to go. Just this one. There's a little picture, and we're done with that one. Okay, let's jump to some more graphing. Don't we all just love graphing? There's the x-axis. There's the y. We are going to have 1, 2, 3, 4, 5, 6. And on the left-hand side, 1, 2, 3, 4, -5, and 6. No commitment to the y-axis hash marks. Okay, and here's how the problem's written. We have a vertical asymptote. Hope you still remember your rational functions. Or, I guess in slightly better terms, rational, because again, it's just a ratio between two polynomials. So the other vertical asymptote is here. And then the actual function is something like this. Beneath the x-axis, going downwards. And then we have one right here. Unfortunately, I think this is actually committing to the problem, but we're not gonna precisely point out where this hits the x-axis. So I'm just gonna put it kind of vaguely right there. And then just goes all the way across like that. Don't forget, we can cross horizontal asymptotes locally, not in end behavior long-term wise. And then right here, there's a certain symmetry to the graph, right? This is kind of rotational symmetry. This one's like right here. This is doing the cubic situation, and so it's going to be something like that. All right. So there is the graph of the function. A lot of information. So if you have experience working with these ones, just go with the usual strats. So there it is. The graph of f of x is shown right there. Which of the following could be the equation of f of x? So we have yet another. Which one could it be? So let me put the choices, and then we're just going to work through each of them. Some choices are a lot easier to eliminate than other ones, of course. It's going to take a while. I wish I'd pre-written these on the actual board. That's okay. VOD users always skip. So we have x plus 1 right here, and then we have x squared minus x minus 6. Option C, we have x plus 1. Oh, so everything seems to be x plus 1. All over x squared plus x minus 6. So we have some sign flipping shenanigans, and then we have choice D. Aha, we have 1 minus x. All over x squared minus x minus 6. Okay. I should probably write down the instruction real quick. But let me just beautify it just a little bit. Move this over like right here. Cut off this loose ledge. Okay. This function is called f of x. Yeah, here we go. I'll just keep it simple. F of x is equal to which one? A, B, C, or D, or none of the above, or multiple answers, right? So here's the overall screen. So what to do? How do we get started with a problem like this? Well, long-term end behavior looks like a good way to go, and then also paying attention to the vertical asymptotes. Yeah. So make note, for this end behavior in particular, it is above the x-axis. So basically, As x approaches a huge positive value, then the y values, or f of x I mean, the y values f of x are going to be approaching 0. But here's the thing though, since we are above the x-axis, just put above 0. Slightly above 0. And of course for this particular end behavior, we are below the x-axis, so we can write it as x approaches huge size negative values, then f of x approaches what? Also approaches 0, as what's happening on the right hand side. But we are below the x-axis, so it's below 0. Slightly below 0. And of course we have the vertical asymptotes. Vertical asymptote number 1, x is equal to -2. And then vertical asymptote number 2, x is equal to +3. So let's check to make sure these things are good, right? Okay. So if we're looking at choice A first, let's evaluate the situation. Let's check the end behaviors first, because I think that will allow for an easy elimination maybe. So leading term on top is just going to be x. Bottom leading term is negative x squared. So what happens in the long-term end behavior? So for sure, this one, the horizontal asymptote, is going to be y equals 0. Horizontal asymptote. Because following the algorithm, there is technically an invisible x power 2. So 0, once we match this exponent with this exponent, we just divide the coefficients. So 0 divided by -1 is 0 for the horizontal asymptote. Alright, but are we above the x-axis? Are we above this horizontal asymptote for long-term end behavior? Well, let's double check. So we can imagine that the top one is going to grow at a certain rate, but then the bottom one will grow at a faster rate, right? So that is true. So the approach of 0 seems reasonable. However, because of the signage, right, we have a negative in the denominator. So this bottom number, as x becomes larger and larger and larger, it's going to get squared, and then it would become negative. So the overall situation is going to be a negative value, which is below the x-axis. So this one is going to be below. Because again, this one is the biggest player. It dominates over x power 1. And it also has a negative sign in the front. So if you're not sure what that means, you could just plug in a very large value into x to get an idea of what's happening in the long-term end behavior. So for example, you can pick x is equal to 1 million or something like that, right? Or let's pick 5 zeros. Yeah, so that's going to be 100,000. What happens in the long-term end behavior for that one? So we're going to get 1,000. That will become 1,000 plus 1. I mean 100,000, I mean. Over 6 plus 100,000 plus, minus 100,000 squared. So that's a bunch of zeros. So that's going to be 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So look what happens. So for just this kind of a small value, it is kind of small relatively to, limit situations. So this one is going to be a small 1,000 over this nonsense right here. Okay, so we're going to get a small number, but the small number, what's the overall sign? The top number is going to be positive. This is a small magnitude in comparison to this large size negative. So we essentially have a positive on top and a negative on the bottom. But since it's close to 0, we have to say it's a negative 0 point something. So that's why we are below the x-axis because we still have a negative value according to evaluation of choice A. So what does that mean for us? It means A cannot possibly be the correct situation. So by analyzing the horizontal asymptotes and behaviors, A is incorrect. So checking this one, of course, it's going to be similar to this one. So we have a positive x power 1 on top, positive x power 2 on the bottom. So this is already looking pretty good right off the bat because it's consistent with this above behavior and then this below behavior. Let's double check that, of course. So what happens when, well, first things first, the horizontal asymptote is still going to be y is equal to 0. That's fine. So are we above or below when we have x approaches positive infinity? So when x approaches a huge size value, the top number is going to be positive, but it pales in comparison to the size of this large size positive. So we're going to have a huge number on the bottom, which I will represent using this thing, and then we have a squared on the bottom. So this whole thing is going to be positive, but it will be close to 0. So I'm going to write it like this, positive looking 0, 0-ish. Which is consistent with what we're given right there. And then we're going to see an agreement in behavior when x approaches negative infinity. So when x approaches a large-sized negative value, the top number here will be negative overall. But the size of that will pale against this x squared. So what happens when we input a negative large-sized value into the squaring? It becomes positive. At least for the bottom part. So this negative doesn't cancel with the negative above. This negative cancels with the squaring. So we're going to get something similar to that one. A huge number squared on the bottom with still a negative on the top. So overall, it's going to have a negative sign, but because we're dividing by an absurdly huge number, it's close to 0. So it's negative 0-ish. Which means we are below, which is consistent with this one. So B looks pretty good. But we need to check the zeros. Because we have, we need to check the vertical asymptotes. So we have a vertical asymptote at -3 and +3. So let us factorize this one real quick. So it factorizes into what? 2 and 3. The larger of the two is negative. So 2 and 3. So this is the larger of the two magnitudes, so it gets the negative. This is the smaller of the two, so it gets the positive. Is that correct? Yes. Yeah. So choice B looks to be correct. But we're not done though, of course. We need to check the other ones as well. Let's look at choice C. Choice C is almost identical to choice B, but the difference is the change in the signages. So the two signs are different, but the larger of the two is positive. The two signs are different, but the larger of the two magnitudes is negative. So this one is going to be wrong based off of the zeros. Because if you factorize this one, it's just going to be this one. But the signs are flipped. So it's going to be x plus 3 times x minus 2. Because again, positive 3x plus negative 2x gives us positive 1x. This one is inconsistent. It's not there. This one right here, this one right here, it's supposed to be there. So choice C is wrong. And then lastly, we have choice D, or choice D. For the most part, again, it's similar to choice B. The only difference is we now have x minus 1 right here. That's kind of awkward. And then for this one right here, it's going to be the same in the bottom. So these vertical asymptotes will be the same as the vertical asymptotes for that one. But this one is different from this one, right? So we have a negative. So because we have a negative on this x, it actually affects the end behaviors. So in fact, what happens is this one is going to get below the x-axis, and this one will be above the x-axis because of this negative difference. So in fact, I think the whole graph just gets flipped over in this particular situation. But just from an end behavior analysis, let's see what happens again. So as x approaches a huge size positive value, what happens? This top portion here, 1 minus absurdly huge, gives you a negative value up on top. But you're going to have absurdly huge squared. So this one outgrows this one. So the bottom portion here, we're just going to symbolically represent it with this huge infinity. So what this means is that it's going to approximate close to 0, but it will still be negative. So it's negative 0-ish. And for graphing purposes, that means that we should be below the x-axis, but this is above. So for that very reason, we can eliminate choice D. So it basically just leaves with choice B, but honestly, choice B isn't even the best answer anymore, because if you think about it, we're supposed to have an x-intercept. I'm going to color that green real quick. So we're supposed to have an x-intercept at x is equal to negative 1. Because negative 1, because if you have negative 1 here, plus positive 1, that should give us y value 0. But this negative 1 is above here, so I didn't do a good job of drawing this graph. So technically choice B is eliminated as well because of the improperly placed 0. But remember in the beginning I said that I'm just going to fudge that one. I'm not paying any particular attention to this one. So by technicality, choice B is also incorrect. But let me fix it so we actually have an answer. So let me clear that. Let me clear that. And let me fix it so that it's going to be a valid response. So right there. So we'll have plausible deniability, which is going to kind of fudge it like this. Oh my goodness. Can't do it. Okay, there we go. Okay. So plausible deniability. So you notice I didn't explicitly put like a dot here. But it should be choice B. I think we're good to go. Technically, we should probably verify these up-down behaviors close to the asymptote. But for now, I'm going to say that the answer is good. I'm going to check one pair of those ones. I'm going to check this one, and I'm going to check this one. But technically, we're done with the problem. So this is a vertical asymptote, which means that we cannot plug in negative 2 directly into our function. So the idea is we plug in something very close to negative 2. So we plug in something like negative 2.001, and we'll plug in something like negative 1.999. That's the idea anyway. So let me copy paste option B. Put it right there. Okay, we're just evaluating the behaviors around the vertical asymptotes. So if we can't plug in negative 2 again. So if we are below negative 2, like negative 2.001, what happens? Will we agree with this exploding downwards behavior? So let's see. So if we have close to negative 2 plus 1, we're going to get like negative 1 in the numerator. And then if we have close to negative 2 inside there, well, let me factorize this again real quick. So the idea is, hold on, let me put it in factored form. X minus 3 times x plus 2. It's easier for me to analyze it if it's in fully factored form on the bottom, because you can see which factor approaches 0, which I think is more informative than having like standard form. Alright, there we go. So again, we're approaching close to negative 2. So if we have negative 2-ish minus 3, that's a clear negative 5-ish. if we have negative 2-ish plus 2, this is where we create a close to 0 situation. So it's not quite 0, but it's close to 0. But in fact, the magnitude is slightly above 0, but it's still negative. So that's like a negative-ish 0. So this one, these two signs cancel out. So we essentially have a negative value. We essentially have a positive value over a negative almost 0. So this is basically going to be negative infinity approach, which is in agreement because it explodes downwards forever. So that looks good. So let's test the other situation on the other side of the asymptote. So we're done with this one. This one checks out. Now we're checking this one. So if we have x value getting closer to like a negative 2, the top portion again becomes a clear negative 1. Again, close to negative 2 minus 3 is a clear negative 5-ish. But again, here's where the interesting thing happens. If this value gets close to negative 2, but it's slightly smaller size than negative 2, we get close to 0, but here's the important part, it's still positive value. So you can see this sign here cancels with this sign, so it's going to be both positives. So we're going to have something like a positive value over a 0, close to 0 situation. So this whole thing we can say that the y values explode in the positive direction, which is in agreement with this one. So that's probably good enough, honestly. We can do the same analysis for this side as well, but again, I think it's going to be superfluous. So we're going to call it for this particular problem. There's the entirety of it, so we're good to go. I'm just trying to find an interesting problem. Let's go back to the log interlude. And again, hopefully it's more interesting than the previous ones, but we'll see. We'll see. All right, we have log base 6 of 11x minus 4. Close the parenthetical, and then we have minus 2 log 2. And that is equal to log of 25 plus 1. There we go. Let me make sure it's copied correctly. Yeah, okay, looks good to go. So here is our problem. Some notes to make. We have log base 6. We have just log. So remember, if you don't see a number, the invisible number is 10. So that's log base 10. This is log base 10. So we should probably get this one to the other side. And who knows what to do with this one. So let's just do it like that. So we're going to plus 2 log 2 to both sides, because we want to group log base 10 with log base 10. Let me just show the aftermath. Let me not do the full visual operation. So let me just copy paste this entire junk again. So we're going to add positive 2 times log of 2 to both sides. So it ends up on that side with a positive. So let me make room. Let me put it close to log base 10 of 25, like this. That way it's a lot easier to make note of what's going to happen between those two. Alright, so again, we're transitioning from first line to second line, and all we did was we added this one, positive 2 times log of 2 to both sides. So this one ends up being on that side, right there. Okay, so again, these two are not combinable. I feel like I've just done this problem very recently. Maybe. Okay. Well, these two are combinable because this is log base 10. This is log base 10. But this one has a coefficient in front, making it awkward. So we're going to do reverse exponential slammage. Take this coefficient. It now becomes the exponent. There it is. And then 2 to the power of 2. We're just going to simplify that into 4. So that's nice and clean. And now that we have a clean term right there, this is log base 10, this is log base 10, so we can combine by multiplying the arguments because it fits the template for the algorithm. So 100 times, so 25 times 4 is 100. And just copy paste this one. There we go. And don't forget, this is log base 10. I'm going to write it explicitly there. 10 to the power of what gives us 100? 10 to the power of 2 gives us that. So which means that we can change this whole term right here into just positive 2, which is combinable with 1. Alright, so here we are. This one, we just might as well consolidate that into a nice clean 3. And now we just exponentiate. So we take this 6, raise it to the power of 3. It should be equal to the argument. What is that nonsense? 6 times 6 is 36. And then 36 times 6 is, what is that? 90, 108, 106? No. What am I saying? 90 plus 30 is 120, right? 126. That feels wrong. Maybe I should actually show my work. Hold on. I can't do math right now. So we have 6 times 6, which is 36. And then 6 times 3 is 18. Oh, I was really off. 216. Alright. So that is 216. So we'll plus 4 to both sides, thereby generating 220. And now we get a nice clean answer. Divide both sides by 11, so x is equal to 20, right? Yeah, 20. And we should be done with this particular problem. Nothing too difficult. Basic log operations. There's the full thing. Double check the domain issues, of course. This is 20. Is it okay to put it in there? Yes, because this one will become a fully positive input. So the answer, x is equal to 20, should be good to go. Alright. Let me check the time real quick. Okay. Not too bad. That is a very interesting problem. Okay, well, let me put it down. So we have here 16x. No, this is not the one I want to do, I'm sorry. It's going to be x minus 1 to the power of 2, and then that's multiplied to 1 minus x cubed. And that is minus 243. And that is equal to 0. Alright. So we have something interesting going on, a little bit interesting. We have here this kind of a mess. This particular base looks similar to this base. The only difference is the signage swap. So we have a plus minus situation. Plus on the x, minus on the 1. We have a plus on the 1, minus on the x. So can we play around with that? And the answer is yes. And the reason why we want to potentially play around with this particular part is so that we can generate x minus 1 as a base, and that one would be combinable with this one. But the only question is it the optimal thing to do? I think it is. Otherwise, you're just going to have to distribute this entire junk right here, and then you have to do synthetic division. So I think this is a specialized situation. So we should probably treat it as such. So that's the plan anyway. Alright, so here we go. We're going to transform this one. We're going to factor out a -1 from those two inside terms. So we're going to factorize it into -1 times x minus 1. But these two factors are embedded within this exponent 3. So I'm going to put brackets just to make it clear. Alright, and then you just copy paste those other two items. Okay, so here's where things can potentially be interesting. This is just going to be distributive property of exponents. We have factor number 1 multiplied to factor number 2. So because it fits the requirement, we could distribute this exponent to here and to there. So let's do that. So we're going to get -1 to the power of 3. And then we're going to get x minus 1 to the power of 3. So that's clearing the brackets by distributing the 3 exponent. And then we have copy paste this one. And copy paste those two. So a few things to make note of. -1 cubed is still going to be -1. So I'm going to move it to the front like that. This base here matches that base, so since this is multiplication all around, we're just going to summate the exponents. So it'll be x minus 1 to the power of 2 plus 3, with a negative in front. And of course there's still a negative right there. Okay, so that's kind of interesting. I think what's going to happen is, again, we're going to avoid the binomial expansion, and rather than do that, let's just move everything over to, let's just move this entire thing to the right hand side. So we're going to get -243 is equal to, add this to both sides, so we're going to x minus 1 to the power of 5. I don't like the way this is orientated, so I'm just going to swap the sides. So it'll be x minus 1 to the power of 5 is equal to -243. So in this situation, we can't directly match the bases since that's where we have our unknown. So we could potentially match the exponents. This is exponent 5, this is exponent 1. This is probably factorizable. This negative is okay because we have an odd powered exponent. So negative outputs are okay from this side. Okay. So what is this? 2 plus 4 is 6. 6 plus 3 is 9. So this thing is divisible by 3's. It's probably 3 to the power of 5, let's be real. But let's check. So divide by 3 is 81. And then 81 is just 9 times 9. There are 2 3's in there. And there are 2 3's in there. Okay, so yeah, the hypothesis was correct. So we have -3 to the power of 5 on the right hand side. This is just copy paste. And because the exponents are odd, we can therefore just say that the arguments are the same thing. Technically we could slap parentheses around like this. Because negative values, as you saw earlier, right here, there's a negative value. We could just have factored it out and put it in the front. And this is the reason why we can do it. This step right here is the reason why you can take this thing right here and just factor out -1 from an odd powered exponent. So by that same token, this negative here, we can think about that as the argument in total for this exponent 5. So therefore, this argument number 1 is equivalent to argument number 2. Because again, odd powered exponent, we don't have to worry about plus minus shenanigans, so we can clear it like this. And final answer, x is equal to -2. Is that a valid response? Yeah, seems pretty reasonable. Basically, this is a polynomial The domain has no restrictions, so our answer looks like it's going to be good. So let's move this for a full screen display. There it is. Full screen display. So no problems with this particular one. Okay, this is kind of a funky problem. I hope it works out. You'll see why it's kind of funky. So we have a line with a slope of 2. So a line with a slope of 2 intersects something else. Intersects a parabola. And that parabola has a vertex located at 3, -3 on the xy axis. Coordinate plane, I mean, xy coordinate plane. Just to have the formal speak, you know? And then what else we have? Oh, this grammar is kind of complicated. A line with a slope of 2 intersects a parabola, parentheses, with a vertex at 3, -3 on the xy coordinate plane, close parentheses, at the point 6, 6. So let's make sure we understand the grammar. Let's do that afterwards. Let me just fully write out the problem. Determine the other point of intersection, if any. Kind of a weird question. Alright. So let's see if we can understand what's going on right here. We have a line with a slope of 2. So from a grammatical standpoint, we have the main action between a line. The rest of this is just modifiers, right? So a line. What kind of line is this? It's a line with a slope of 2. So this is just extra information. So a line intersects a parabola, and then this parenthetical itself is also just a bunch of extra information. So for analytical purposes, we can just ignore it for now. So the basic sentence reads, a line intersects a parabola at 6, 6. Okay. Good to know. And then what? Determine the other point of intersection, if any. Okay, well, okay, it's not too bad. I thought it was worse than what I had initially evaluated. But, so we have a line with a slope of 2. So y is equal to mx plus b. Classic. So that's going to be the line right here. It has a slope of 2. We could use point slope form, but it doesn't matter. It's just 6, 6. So 6 output if the input is 6. And that allows us to solve for the b for the linear function. So b is equal to -6. So thus, the linear function is going to be y is equal to 2x minus 6. Just spot check that. 12 minus 6 is indeed 6. So this checks out. Okay, and then of course we have the other piece of information. We have a parabola, and the parabola has a vertex at 3, -3. So all we have to do is write the equation for the parabola. skeletal equation. We have some sort of amplitude. We don't know what it is, but because we're given the vertex, we can use it to populate this one. So x minus 3 squared, then minus 3 on the outside. So that's vertex form. Unfortunately, we don't know the a value right away, but we are given this point. Since the line intersects the parabola at 6, 6, then 6, 6 is part of the line and it is part of the parabola. So therefore, this x value and that y value works for the parabola. So let us populate that as well. So we have 6 is equal to a 6 minus 3 squared minus 3. So typically when you're given points for a problem involving functions or graphs, that means you could just plug them in. And that's, if you have no idea what to do, plugging in usually helps. Alright. So here we go. We have a 6 minus 3 is 3. 3 squared is 9. We're going to add 3 to both sides. So the a value is a clean 1. Alright. So that means that our parabola is going to be 1 times x minus 3 squared minus 3. And that's next to our linear function. Right there. What are we supposed to do? I kind of forgot. We are supposed to determine the other point of intersection, if any. Oh, okay. Okay, that's not too bad. How do we do that? Well, this is basically a system of equations, and when you have intersections, that's when the two functions are equivalent to each other. So mathematically, we would set the two functions equal to each other. Basically, for what values of x's do the two functions have the same y input? Because that's where they're going to meet up. So mathematically, all we need to do is set the xy's equal to each other. So here's the idea, right? This is going to be some sort of parabola. Oh, let me put it in the right color. So if you decide to graph this thing right here is going to look something like this. And then you have a linear function. It's going to intersect right there-ish and then right there-ish. So at this particular point, they share a common x and y. And then at the other point of intersection, they also share a common x and y. We're already given one of them. The first one occurs at the vertex. Oh, interesting. Well, no, I'm sorry, at 6, 6. So that's probably this one right here, right? 6, 6. So our job is to find the other one, which just involves just setting. And again, since they intersect the same location, that must mean that this y is the same as that y value. So let us just set them equal to each other. So smashing those two functions together. So we're going to get this one equals that one for the setup. Because again, at this particular intersection, they share the same x and the y. So that's the setup. Again, this one is there, and then that one is there, because this equals that at the intersection. This is just binomial expansion. Use your favorite algorithm. That's the expansion. Copy paste the -3. Copy paste those other stuff right there. So this is going to end up being a quadratic situation. So set up for zero product property by moving everything over to that side. So x squared has nothing to combine with. Minus 2x, minus 2x. So it'll be minus 8x. Plus 6, plus 6. So that's going to be 15 minus 3, which is 12. Okay, things are getting kind of cramped on the bottom, so let me move things upwards. Alright, it seems like a pretty nice situation. We have a nice looking quadratic. It looks perfectly factorizable with a 6 and a 2 right there. So we have x and a 6, x and a 2. The signs are the same, both are negative. Yeah, this is a negative 6, this is negative 2x, so that's going to be 8x. Negative 2 times negative 6 is positive 12, yes. So two answers. We have x is equal to 2, x is equal to 6. What does that mean? It means that when x is equal to 2, you have a common intersection right there. And then the 6 refers to the first point of intersection that was given from the problem. So when x value is equal to 6, the y values both agree at 6. So that's the one we don't care about because we already have that given. So this is the other one that we have. So at x value is equal to 2, the parabola will intersect the line at that location as well. So do we need the point? Yeah, we need the point. So this is just the x-coordinate, so let's ignore this one. So we're just focused on this one, so we need to plug that back into the equation. Always plug it into the easier one rather than the more difficult one. So we have 2 times 2, which is going to be 4. 4 minus 6 is negative 2. So the corresponding y value is negative 2 at this second point of intersection. So I kind of drew this wrong. This is supposed to be below the x-axis like that. But that's just a sketch. Okay, so that means that the other point of intersection is at 2, negative 2. Take a step back. There's the overall thing. This is the answer, and we are good to go. Alright, this log problem doesn't look too difficult, so I guess we're just going to do it anyway. I think the log problems I did the other time, like maybe 2 or 3 streams ago, was more difficult. But that's okay. So we're going to have log base 3 of 3x plus 3/10. And that is going to be equal to log base something. Log base 2 of 32. Well, you could already see this is transformable. Minus log base 3 of x plus 2. Alright, so that's the problem. Again, this one's already transformable. This is base 2. That's fine. This is base 3. This is base 3. So we should probably move this to the other side. But let's first deal with this chunk. 2 to the power of what? Gives us 32. It must be 5. So this whole term right here transforms into just 5. This one we're going to move to the other side by adding it to both sides. So take that one. Whoops. Take that one, and then we'll add it to both sides. Just moving things around real quick. So that's a plus. And the equal sign remains right there. So just to summarize what has happened, we transformed this log base 2 of 32 into 5. This one we added it to both sides, so it moves over right there. And the reason why we wanted to move it there is because this log base 3 matches with that log base 3. There's a plus in the middle, so this is a prime candidate for condensation rules. So just multiply the two arguments together. So use your favorite distributive property. We're going to get 3x squared. This is kind of awkward though. So plus, unfortunately it's a fraction. So we have 3/10 x plus 6x. And then lastly those two plus 3/5. So all of that is inside the argument for the log base 3 function. Copy paste the right hand side, which is just a 5. Okay, there we go. Again, not the nicest looking situation, because this is awkward fraction, this is awkward fraction, but that's fine. We'll clear it afterwards. We're just going to take this 3 raised to the power of 5. What was 3 to the power of 5? We did this like maybe 2 problems ago, but it's going to be 3 times 9 times 9. That's 81 times 3, which is 243, yes. Alright, we'll copy paste the entirety of the inside. Is it worth trying to combine these two? Not yet. Okay, so here's what's going to happen. I'm going to propose multiplying both sides by 10, just to clear fractions. So we're going to get 30x squared plus 3x, because this one distributes to this one, thereby canceling the denominator. So it's just going to be 3x, and then plus 60x, so it'll be 63x. This 10 distributes to that one, cancels partially with the 5, so 2 times 3 is 6. And then 10 to that one is easy. Just add an extra 0. Okay, I'm not sure if that's the best idea, but let's move this over to the other side. I hope this works out. I don't know, I'm kind of wary about the numbers, so it's going to be 24, 24. That's weird. Oh, almost screwed up. It's a negative because we're subtracting 2,430 from both sides. Very sloppy. Don't be like me. Alright, this is divisible by 3, as is that one, as is that one. So let's clear the 3's first. That's kind of weird. It's going to be 8, 0, 8. Alright. Do we have any other things to factor out? Not that I can think of. This is not divisible by 7, but this one is divisible. This one only has 3's and 7's. This has neither the 3 nor the 7. So nothing further to divide. So let's just get straight to our favorite factoring method. According to discriminant test, because this is negative, it's going to guarantee to have real solutions. So let's hope we pick the good ones. So this 10 and 1, probably not that one. 5 and 2, probably that one. That's kind of weird, right? It's going to be 101 times 8. Is that it? Interesting. Oh, you know what? It actually is this one. Wow. So not this one. So this combination with this one, we get an 80 potentially. And then we get a 101. So if we subtract that, that is in fact 21, which gets us this one. Perfect. Okay. That's good. It's good that it worked out. I was kind of worried for a second. So we have a 10x in the front. And that 10x gets multiplied to the 8 on the other factor. And this 1x gets multiplied to the 101. So 1x gets multiplied to the 101. Let me give it a little bit more space. Let's just make sure those signs match up. The two signs are different, and the larger of the two magnitudes is positive. So this is the larger of the two. Smaller of the two. Okay, so we have two answers. We have x is equal to negative 101 over 10. And then we have positive 8 as our answer candidates. But this is a log problem, so always go back to check the domain. Alright. So which answers will work out? This one is like a little bit close to negative 10. So if you add negative 10 to 2, this argument becomes negative as a whole inside this log. And you can't have that in log functions. So therefore, this is extraneous. Check the 8 as well. That gives us a positive argument. That's okay. Gives us a positive argument, so that's also okay. So we only have one solution. It's going to be x is equal to 8. Alright, let's take a step back. Unfortunately, I can't get the whole thing in. It's fine. It's going to be like this. So that's the whole summary of the situation of what has happened. X value is equal to 8, and we're good to go with this log problem. Okay, I think the title indicates the radical function, so we better do at least one radical in order to not have a clickbait title, right? Okay, so we have another problem. Another graphing problem, I mean. Here it is. It's kind of a ridiculous longitudinal looking problem. So we have this little tiny arrows here, tiny hash marks, and then we have 1, 2, 3, 4, and 5 with half hash marks right there. Like so, and then we have 6, and then we have 7. And we actually do have a vertical asymptote this time. I mean, not asymptote, we have a vertical hash marks this time. This is going to be 1. This is a half hash mark. This is going to be 2. Half hash mark. And then in the other direction, we have -1 hash mark. Alright, already looking gorgeous. So here is the tip, just the tip right here. Alright, here's where it's going to get a little artsy. Wait, let me see. I can't see very well in the dark. It's kind of dubious. Okay, but I think there is another point at one space over, but it's like right here. So I think it's right here. Okay, and then we have another point at 7, comma 1/2. So right here-ish. Yikes. Okay, so I'm not committing to where it's intersecting the x-axis, so I'm going to put the x-intercept is ambiguous. Just to cover my bases real quick. So x-intercept is ambiguous. Alright. So I think that's it. So we're given this particular function. This function is called f of x. This is an arrow indicating long-term end behavior. It ends here. That's where the tip is. So this is f of x. So the graphing is done. And let's get to actually looking at the problem. What is the problem? The graph of x, f of x is given above. Sure, determine the value of x when f of x is equal to 1. Alright, so basically f of some constant value a, some a input is going to be equal to 1. So our job is to figure out a is equal to what? And that's it. Alright, so that's fairly interesting. So if we were given a good graph, all we need to do is trace. So here's +1, so if we trace it, unfortunately our graph is too short, it goes off screen. So this one right here is at 1/2. So I'm telling you this right now, this one right here, the way I've drawn it, it's supposed to meet up at this particular point, right there. So that point is 7, comma 1/2. This point right here is going to be -2, comma -1. And this point right there, that point is -1, comma -1/2. So we have 3 points. We should be able to generate the equation of this particular radical function. Yeah, it's going to, I should specify that f of x is specifically, it's going to be just exponent 1/2. So it's just basic radical. So it's not something like a fourth root, for example. Let's just keep it simple, so we won't have any wiggle room for argument. All right, so we have 3 points. We have the plot, we have the tail, we have the tip right here. So this is the most important one. I'm not sure if it's called a vertex again, but let's just use this one to generate our skeletal equation. So we can define f of x as equal to some sort of amplitude in the front. We don't know what it is at the moment. We could probably count spaces, but let's avoid that for now. And then we have skeletal equation is going to be square root of x. We're going to use this one for the x value, like a vertex, and then we'll use this one for the y value. So in here we have minus 2. That's coming straight from the x value. And then out there we have a negative 1. So if it's inside the function, it's always minus. I mean, it's always opposite sign, so it becomes plus. And this one keeps the same thing. Most of the time. Until you get to conic sections, then you have to group it with the y's. And once you group that lone number with the constant with the y, then you have to do opposite rules for the signages. It's very consistent though, in my opinion. Okay, so we have something like this. Unfortunately, we don't know what the a value is. That's what the other 2 points are for. We could use this point to slam dunk those values into there and there. Or we can use those points, slam dunk them there and there. So, which one will it be? We could actually count spaces to get the a value, but let's just do plug and chug. So let's take the second point and plug them in. So let me colorize this real quick. So this is going to be -1, which we will plug into there. And the output will be -1/2, which we'll put right here. Okay, so for that particular point, that will allow us to solve for a. Always pick the nicer points. They're technically both nice. So this one becomes 2 squared of -1 plus 2 is +1. Square root of that is going to be +1. So copy paste. So +1 to both sides. So a is equal to 1/2. And then there we go. We can populate the full equation now. So f of x. We just figured out that the a value is going to be 1/2. And we already have the skeleton of that from the tip information. So x plus 2 minus 1. So that should be the function, the equation of the function. We could always do a quick test. So quick test time. 7 should result in 1/2. So 7 plus 2 is 9. Square root of 9 is going to be 3. 1/2 times 3 is 3/2. 3/2 minus 1 is going to be 1/2, which checks out. So we have great confidence that this is the correct equation for f of x. What are we asked to find? This thing. Right there. So we are told that there's an a input will result in a 1 output. So a input should result in, what was it? A 1 output. Alright, so there we go. This is going to be f of a. So the a goes into the argument for the x. It will be modified by +2. And then we have a -1 should be equal to 1. So this translates into that. Standard situation, all we need to do is now solve for a. We need to add 1 to both sides, multiply both sides by 2, clear the exponent, and then clear the +2. So +1 plus 1. Kind of tedious work at this point. Thereby getting that one times 2 times 2. So this one clears from the times 2 times 2. Alright, so we get square root of a plus 2 is equal to 4. classic square root situation, so thus we're going to square it as the inverse, but we have to square both sides. So clearing the square root, we get a plus 2 is equal to 16. So minus 2 minus 2. So a value, not the amplitude, I'm sorry, I'm using the same letters. So a value is equal to 14. So thus, a value is equal to 14. Not to be confused with the amplitude, I'm sorry, I used the same letters. I should not have done that, but too late now. But at least we have the answer right here. Should be good. And then we are good to go for this particular problem. Alright, I guess we might as well do maybe one or two more. We have here g of x, the function situation, g of x is a parabolic function. What about this parabolic function? With a minimum value, interesting. This is a key phrase, a minimum value. And then calculus people will be well versed with minimum values. So g of x is a parabolic function with a minimum value of -1. End sentence. If g of -2 is equal to g of 8, without either of them being 49, what is the equation of g of x? I have a feeling this one gives a little bit more information than it needs to give, but that's okay. So we have this thing equals this thing equals 49. That's particularly interesting. It's a parabolic function and a minimum value. So we have multiple tiny little clues. So number one, this is just a parabolic function. Number two, minimum value of -1. This means something very specific. So when we see the word minimum value for a parabolic function, that means that our function opens upwards, like so, upwards. And the vertex is the lowest point possible for the parabola. And this vertex point, we can denote it using HK standard notation. So since the minimum value is -1, that implies that this vertex coordinate, the y value of k, it has to be -1. So that is the direct translation. A parabolic function with a minimum value of -1 means that the lowest possible which means the lowest possible y value is -1, which means the vertex coordinate y value is going to be -1. Okay, so that's nice. We're also given this piece of information right there. So this is now a separate piece of information, but there's something you have to remember, and if you remember it, it'll make the mathematics a lot easier for doing these type of problems. And the thing to remember, the nice thing that if you can remember it, please remember it, is that the parabola is perfectly symmetrical about its axis of symmetry, which pierces straight through the vertex. What that means is if you travel a certain distance to the left, you get to a y value. If you travel the same distance to the right, you get the same y value. Which is what this is basically telling us right here. So if you travel to a certain -2, a certain number of spaces away from the axis of symmetry to reach -2, then the y output is going to be 49. And that's the same thing you do if you travel to the right to reach 8. Then the y value there is also 49. So let's exploit the symmetry, because again, it's equidistant. The totality of this is going to be a travel distance of 10, because 8 minus minus 2 is a total distance of 10. So between the number that is between -2 and +8 is going to be +3 in the middle, because 3 is plus 5 to take us to 8, and then 3 minus 5 will take us to -2. So that means that the axis of symmetry, which pierces through the vertex, should have a coordinate of 3. So we know h, we know k. We're given an explicit value right here, so we can actually come up with the equation of g of x now. So let's start with the vertex and the skeletal equation. So y, or rather g of x, is equal to some sort of a value. We don't know immediately what it is, but we know it's going to be x. What's the vertex? The vertex is at 3, so x minus 3 will give us 0 squared. All right. And then the k value on the outside is going to be -1. So that is our skeletal equation. We need to figure out the a value, but that's why we're given 2 points. This is point number 1. And then this is point number 2. Let's pick the easier, smaller number. So it's -2, comma 49. So we will take that instance and put it into the function. So again, if the x value is -2, the y value is +49. So the y value will be +49 if the x value is -2. So that means for us is after we perform the substitution, considering the point containing the point at -249, we should just plug it in. And that will leave us with just one unknown, which means we just got to crunch the numbers. So +1 plus 1. -2 minus 3 is 5. -5. -5 squared is +25. And thus we get a very clean a is equal to 2. So that's cool. So I think we have enough information. We can put them all together. So taking the skeletal equation, put it right there. We've just figured out that the a value is 2. The amplitude is 2. And that's all is required to do the problem. What is the equation of g of x? Well, there it is. Should we follow form and just make sure we do a quick test? We probably should, so let's do it real quick. So we use this point to generate the a value, so let's use this other point to test our hypothesis. So if x's value is equal to 8, then the y value should be +49. So plug in the 8. 8 minus 3 is 5, so that should work out, because we already did it with -5. So 5 squared is 25. 25 times 2 is 50. 50 minus 1 is indeed 49. So this pretty much clinches it. So take a step back. So overall, that's the situation. It checks out. We should be good to go. Alright, so that takes care of the radicals. I think we've hit all the problems. We've hit the log type function problems. We've hit the radical. We've hit one. We've hit a single radical problem. We've hit multiple graphing problems and polynomials. So I think we can conclude it for today. I think it's been 2 hours. So I think next time up for the next stream, we're going to be covering probably trig functions, because I have a folder full of mixed problems where I mixed up problems where problems involve both trig functions and log problems. So I think that's going to be a long session. Yeah, there's going to be multiple. It's going to be a pretty long string of streams for trig functions because they're pretty involved. Yeah, so basically SOHCAHTOA, sine functions, triangles, We're going to have right triangles, non-right triangles. Yeah, I think I have to redo one of my earlier streams from a long while ago. Well, technically it's not a stream, it was like a video, but that's the plan anyway. But that's it for tonight. I don't think I'll be streaming later. So that'll probably be it. So probably no streams tomorrow either. Yeah, that's the plan anyway. So next time, probably trig functions. Okay, signing off. Y'all have a good one.